On with learning target 4F in this video, and in this video we're going to learn how to divide complex numbers as well as solve for all real and imaginary solutions from a quadratic equation using the quadratic formula. So starting off, let's look at dividing complex numbers. In our prior video we looked at how to add, subtract, and multiply our complex numbers. We also learned about what a complex conjugate was. So as a little reminder, a complex conjugate to a plus bi is when we change the sign on the imaginary term and we get a minus bi. Now we're going to use the concept of a complex conjugate to help us simplify when we're dividing complex numbers. So our goal when dividing complex numbers is going to be to multiply by our fancy number 1, and that fancy number 1 is going to come from the complex conjugate of the denominator. So in each one of these we want to simplify the following to the form a plus bi. And in example 20 we're looking at 9 plus 20i divided by 2 minus 3i. Now as it stands right now, since I have two terms in the numerator and two terms in the denominator, I can't break this apart at all, mainly because of those two terms in the denominator. So to be able to simplify this to the form a plus bi, we still might have fractions, but I don't want to have like two terms over two terms. I want a single term plus the imaginary term. So that real component and the imaginary component I want separate. To help fix this issue, we can use the complex conjugate of the denominator. And the reason this works out is we saw in our prior video, when I take two imaginary numbers and multiply them, if they're complex conjugates, then I end up with a real solution out, or a real answer out of that. And my goal is to change the denominator of this fraction into a real number. So to start this off, I need to know what my complex conjugate of my denominator is. What would the complex conjugate of 2 minus 3i be? So the complex conjugate of 2 minus 3i is going to be 2 plus 3i, since we changed the sign on the imaginary term. And I'm going to multiply that to the denominator, but because I need to keep my problem the same, I also need to balance that out by multiplying by 2 plus 3i to the numerator here. And I'm putting parentheses around everything because I'm going to end up distributing and foiling all of this out. And this right here is our fancy number 1, since I have 2 plus 3i over itself, so that reduces down to just be 1. So we haven't changed our problem since multiplying by 1 is our identity, which keeps our problem exactly the same. From here we want to start foiling everything out. So in the numerator I have 9 times 2, so we're getting 18. Then I get 9 times our 3i, so we're getting plus 27i. Then we have 2i times 2, and that's going to give us plus 4i. And on our last terms we have 2i times 3i, which is going to give us a positive 6i squared. So that looks very similar to what we did in our last video when we were multiplying out. We're going to do the same thing with the denominator. So my first terms of 2 times 2 gives me 4. Then I get 2 times 3i, so I get positive 6i. Negative 3i times 2 gives us a negative 6i. And then negative 3i times a positive 3i gives us a negative 9i squared. So we did this in our last video when we multiplied out complex numbers. Now we're just having to take it a little bit step further with the whole division. So on each one of these I want to simplify as much as I possibly can. So in our numerator I can combine our imaginary terms of 27i and 4i to get us 31i. And on our I squared terms, remember I squared is equal to negative 1. So I'm going to replace the I squared with a negative 1 in both the numerator as well as in the denominator. In the denominator also, we actually get to cancel our inner terms there, which is the goal that we always want to happen when we multiply by that complex conjugate, which allows us to end up with just a real number of 4 minus 9 times negative 1. I'm going to simplify this a little bit more, so we get that 18 plus our 31i minus that 6 over, we get 4 plus 9 in our denominator. Continuing to simplify our real terms, that 8 minus 6 is going to give us 12. So So we end up with 12 plus 31i in the numerator, all over 4 plus 9 is giving us 13. Now from here, I'm still not in the form a plus bi, but I was able to change and make my denominator a real number only, so that what I can do from here is split this up and have 12 over 13 plus 31 over 13 times I. And this will be our final answer. And although I still have fractions, I'm now in the form a plus bi, where a is that 12 over 13 and our b term is 31 over 13. And the whole reason this works out is because we multiplied by the complex conjugate of the denominator, I ended up with just a real number in our denominator of our fraction, which allows me to divide the top portion, the first term plus, and then divide the second term separately. So we get another example of solving and simplifying complex numbers using division. So on this example, we have 2 plus 3i all over 1 plus I. What's the first thing we need to do for this guy? First thing we need to do is identify what the complex conjugate of our denominator would be. So our denominator here is 1 plus I. What is the complex conjugate of 1 plus I? So the complex conjugate of 1 plus I is going to be 1 minus I, and we're going to multiply that to both the bottom and the top part of this fraction. And I'm putting parentheses around this since we're FOILing everything out. And the reason, again, this isn't changing anything is this is our fancy number 1, since 1 minus I over itself is equal to 1, and multiplying by 1 does not change our expression. Why don't you guys pause the video right here and multiply both the numerator and the denominator out, and then let's check that step. So in multiplying out the numerator, we'll get 2 times 1 to give us 2, 2 times negative I to give us negative 2i, 3i times 1 is giving us a positive 3i, and lastly 3i times negative I is giving us a negative 3i squared. In our denominator, when we FOIL out, we end up getting 1 times 1, so we get 1 minus I plus I, coming from the 1 times negative I and the I times positive 1, and lastly we get a negative I squared. From here, we want to go ahead and simplify as much as we can on top, simplify as much as we can on bottom. Why don't you guys pause the video and simplify the numerator and the denominator of this fraction. So let's check our simplification. In the numerator, I can combine my imaginary terms to get just a positive I, and then remember I squared gets replaced with a negative 1. In our denominator, the imaginary terms cancel each other out since I have a negative and a positive of them, and I end up with 1 minus I squared gets replaced with a negative 1. Continuing to simplify from here, we really have 2 plus I plus 3 all over 1 plus 1. So that's giving us 5 plus I in the top all over 2. Our last step here is to rewrite it in the form a plus bi. So our a is going to be that 5 over 2 plus our b term is going to be a 1/2 since the coefficient on the I is actually a 1, and then times that I. And that will be our final answer for this guy. So division and dividing of complex numbers heavily relies on all of our skills that we learned in part 1 of this video, from complex conjugates to multiplying out complex numbers, as well as adding and subtracting them, combining all of those like terms. Now the second part of this video is going to focus on actually solving and finding our real and our imaginary solutions. So we're going to go through 2 of these examples. What I have written down already is just a review from a prior learning target on the quadratic formula. So to review the quadratic formula, it's x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And we're going to use the quadratic formula to solve both of these quadratic equations. And we'll see the instructions are a little different. Instead of just saying solve, they now say find all the real and imaginary solutions. So before, when we got the square root of a negative number, we just said that we had no real solution. which was true. I cannot take the square root of a negative number and get a real answer out. But now that we've learned that the square root of -1 is equal to our imaginary unit I, we're going to actually continue to solve those all the way down till we get our imaginary solutions on here. So let's look at our first example. We have 2x squared minus 3x plus 4 equals 0. To use the quadratic formula, I do have to be in standard form, which as a reminder is a times x squared plus bx plus c. So in this case we are in a standard form, and I'm sorry, since we're solving it, it's not y equals, it would actually be 0 equals that. So that's why I know that I'm in standard form to start off with. So let's identify our a, our b, and our c. Why don't you guys pause the video and write down what a, b, and c are all equal to. So our a is equal to positive 2, our b is that negative 3, and our c is that positive 4. From here, we want to go ahead and set up the quadratic formula. Why don't you guys pause the video and write down your setup for the quadratic formula. And remember, it is necessary to show your setup on a learning check or on an assessment. So let's check our setup. We start off with negative b, so I get negative 3 plus or minus the square root of b squared. So since b is negative, I need to put it in parentheses since I'm squaring both the 3 and the negative sign, minus 4 times our a, which is 2, times our c, which is 4. And I'm going to extend that square root over everything since that's all underneath the square root sign. Then all of this gets divided by 2 times our a value, which is also 2. This is our setup for the quadratic formula, and it is necessary to show this on all of our learning checks and your assessment because it is demonstrating that you understand how to use that quadratic formula. From here, let's start simplifying it part by part. So negative times a negative 3 is going to give me a positive 3, plus or minus the square root. Negative 3 squared is going to give us a 9, a positive 9, and then negative 4 times 2 times a positive 4 is going to give us a negative 32. All over 2 times 2 is giving us that 4. We can simplify this a little bit more underneath the square root. So I still have 3 plus or minus the square root of negative 23 all over 4. So now we've simplified as far as we can from what we've done before. And before we used to say, well, I got the square root of a negative number, so I get no real solution. And that's still true, but we know how to find the imaginary solutions now. So we're going to take this a step further and start simplifying that square root of negative 23. The first thing I can simplify is the fact that since I have a negative, the square root of -1 is equal to I. So I end up with 3 plus or minus I times the square root of 23 all over 4 still. And so that I is coming by taking the square root of -1 and replacing it with the definition of I. And notice the I is outside of the square root by definition. So the square root of -1 is equal to just I, not the square root of I. So that's why we take it out of the square root. Now from here, there's a couple more things I would need to do. I want to make sure my square root is completely simplified. So 23 is not a perfect square, nor does it have any perfect square factors inside of it. So I can't simplify the square root anymore. But my last step I want to do is I want to get these into the form a plus bi. So what that means is I need to break this apart into my real component, which would be 3 over 4, by taking the 4 dividing that first term, plus or minus, I have that I times the square root of 23 over 4. So I've just split apart that division into both terms. But since we want it in the form a plus bi, I need to take it a little bit further, and I'll still have the 3 over 4 plus or minus my b term is going to be the square root of 23 over 4, and then separately, or not separately, but then I get times that I. That way it's just of the form a plus, or minus in this case, our b times our I. And those will be our final 2 answers. And notice we do get two answers out of this. We get 3 over 4 plus the square root of 23 over 4 times I, as well as 3 over 4 minus the square root of 23 over 4 times I. And what's neat about these is we're going to notice we're actually getting complex conjugates as all of our answers, since I have the plus the imaginary as also, and the minus the imaginary part on that solution as well. So lots of this is similar to what we did before with the quadratic formula and solving. Now we're just taking it a step further. When we get the square root of a negative number, we can simplify that using our imaginary unit and then continue to break it apart so it's in the form a plus bi. Let's look at one last example together. So in example 23, we have 3x squared minus 2x plus 2 equals 0. And we're going to solve for our real and imaginary solutions using the quadratic formula. So the first thing we need to identify is what is our a, our b, and our c. Why don't you guys pause the video right here and determine what a, b, and c are. So to check that, our a is going to be positive 3, our b is a negative 2, and our c is a positive 2. Now that we know what a, b, and c are, we can go ahead and set up the quadratic formula from here. Why don't you guys pause the video and write out your setup for the quadratic formula, and then we'll check it together. So our setup, and I'll scroll up so we can see the whole quadratic formula there on the screen, is remember negative b, so we get negative 2 plus or minus the square root of b squared, so negative 2 again in parentheses, that whole thing squared, minus 4 times our a value times our c value. And all of that is underneath the square root. And then all of that, is divided by 2 times our a, so 2 times 3. So double check your setup right now, making sure again that you have the parentheses around the negative 2, because there is a difference between writing negative 2 in parentheses squared. That is not the same thing as saying just negative 2 squared. So we want to make sure that our setup is completely correct, and if we need to have parentheses there, that we write them down. Why don't you guys simplify from here down to the step where you end up with just the square root of a negative number, and then we'll check that. So to check our next step, the double negative makes that a positive 2. We get plus or minus the square root. Negative 2 squared is positive 4. 4 times 3 times 2 is going to give us a 24, so we get minus 24. Oops, I got a little messy. And then in the denominator, we have that 2 times 3, which is giving us all over 6. Oops, there we go. Okay, from here, if we keep simplifying down, we get 2 plus or minus the square root of 4 minus 24 is going to give us a negative 20 all over that 6. From here, we can actually continue to simplify this a lot further. So why don't you guys simplify what the square root of negative 20 is, and then we'll check that together. So to simplify the square root of negative 20, the first thing I can do is take out that negative sign, and remember that the square root of negative 1 is equal to I, so I get I times the square root of 20, all over 6 still. And then 20 itself, although it's not a perfect square, it does have a perfect square as a factor. 4 is a perfect square in there, so I can continue to simplify this, and I end up with 2 times I, since the square root of 4 is 2. That 2 comes out, and I just get the square root of 5 left over inside, all over 6. From here, I'm done simplifying the square root, but I can continue to break this apart, and we get 2 over 6 plus or minus 2 root 5 over 6 times I. So I'm just rewriting it so all that whole b term comes before the I. And I'm almost done. My last thing is to reduce my fractions all the way. 2 over 6 is equal to 1/3. So I get 1/3 plus or minus the square root of 5 over 3 by reducing the 2 over 6 again, and then times that I. And that will be our final answer. Notice here we got two imaginary solutions, and they happen to be complex conjugates again. And that's always going to happen because we have this plus or minus in the quadratic formula. So in the second part of this video, we learned how to divide complex numbers, as well as solve for all the real and imaginary solutions for a quadratic equation using the quadratic formula.